Um, Good morning, everybody. Welcome to Tuesday. So, yes, Tim, I did get the email that you sent over the weekend, and I ignored it because it looked like it was going to involve work. Um, but maybe I'll take another look this afternoon after I've taken my vitamins and so on. Um, anybody else have any questions you want to bring up before we get back into it? Well, yes, Tim, if it does get lost in the pile, send it again. You'll get my attention eventually. Um, yeah, so I said last week that I was going to post a homework, and then it never happened. Um, but it's just about ready to go, and I'll get it up this afternoon. And I want to spend a little bit of time today working on something that is relevant that I'm going to ask you to do in the homework. That is probably not obvious. It has to do. Here's what I want to do, and let me start by showing you sort of the example we want to end up with, and then talk about where it comes from. So I wanted to do an exercise that involves the creation of models, in a sense. And as I mentioned before, the way that you create models in real life is, of course, you have a friend in the design college who knows how to use Blender, and that's where they typically come from. But there's other stuff that is simpler to do that it's good to be able to know how to do on your own, and at least know how these things are constructed. And in particular, the question about where do you get normal vectors, I think, is an interesting one. So a very simple kind of model to generate sort of just by writing a loop and using a mathematical function is something called a height map. So the idea of a height map is that it's just you have your xz plane, and for each value xz pair in the xz plane, you have a y value, which is the height. And you don't do anything more complicated than that. For example, think about a sphere. A sphere is a good example of something that you cannot generate with a height map, because for any given xz pair, you actually have two associated y values, one on the upper face of the sphere and one on the lower hemisphere, as it were. So it's limited, but it can be really useful, and I think it's a good sort of starting point for experimenting how to generate these things, because solids like a sphere or a torus or whatever are typically quite a bit more complicated to write the code to produce. So what we would like to end up with is something. Let me show you. If I share my screen. And I guess we need one of those. I'm not spaced out. I don't know why you think that. Let's see. ISU F19 lighting, no workspace. Lighting. So there's an example of, so this is a wireframe of a height map. And by wireframe, I mean we're simply drawing the outlines of the polygons rather than trying to actually shade them. And what looks like shading here is totally fake. All it's doing is it's using red for the lower y values and yellow for the higher y values, so that it looks like it's been shaded, and you can see the shape of the thing a little bit. But notice how it is simply a function of two variables. There's a height associated with each x and z value, and then we generate a bunch of points using those heights and figure out how to organize them into polygons. So that's where that comes from. And so this is one example of a function you could use to generate an interesting little surface mathematically, just for shits and giggles. We could try something else, like, you could make a hyperbolic paraboloid. And the thing to notice, I guess is not obvious, is that these are really simple mathematical functions, right? This is one line to generate our friend hyperbolic paraboloid, which, oh, here's another trick I have to show you. What did I just do? Hyperaboloid. Why is this not reloading? Am I editing the wrong file? Oh, yes, I am. All right, that explains everything. Yeah, edit this one. I just wanted to show you that you could do something different. Right? So there's another kind of interesting mathematically generated sort of shape. And these get very interesting when we start learning how to control randomness within our programs, which we'll do later on, and generate what's called Perlin noise. So that'll be fun to play with when we get there. So the next question would be, you have a thing like this, and showing the wireframe is really just an exercise, right? It's because we want to be able to have a little visual in our mind of what we've created and where the polygons actually are. And you can see that with a wireframe pretty easily. What we'd like to be able to do is to now make it look like a surface. And in order to do that, right, we need shading, we need to have lighting, and we need normal vectors. And so the question is, well, where do normal vectors come from? And that's what we want to work on. So if I look at height map test 2, what did I just do? I broke something, hold on. Height map test 2, what have you done? Should be a ripple, 10 to 10, test 1 ripple. Oh. Test 2. I'm questioning my sanity. There we go. Oh, that's what I was looking for. So now we've taken that wireframe, in other words, a set of vertices organized into triangles, and we've made it look like this smoothly fluctuating surface. And this is all a trick, right? This is all a trick of choosing normal vectors to present the illusion of a contour, and then using the Phong shading technique to make it look smooth. So, 2 things to think about, and I guess the minor point is, what is up with the wireframes? And that is actually easy. So we talked before about the concept of indexing, right? That you can have, oops, I better erase. Let's try this. Okay, yeah, so you have, let's say, something like this. So you've got some vertices, call them A, B, C, and D. Some numbers, right? Triples of numbers. So you've got your vertex data, and what you could do with this data is you could just create an array with the values A, B, C, D. So this is the vertex data. And you can take a set of indices, which would be an array in the order of, so let me get a marker. So if you look at the buffer that you created, say this is the vertices you actually loaded onto the GPU, you can think of them as having an index. And again, each one of these is probably 3 actual floating point numbers, possibly 2 in the case of a 2-dimensional thing like we did at first. But think of it as 3 floating point numbers, but they're grouped. In other words, you always tell the GPU when you look in this buffer of data, each vertex is represented by 3 numbers, 3 floats in particular. So what if you want to draw that quad? In other words, you need to go A, B, C, and then A, C, D. And you can do that with indices, right? So your indices would be 0, 1, 2, 0, 2, 3. And that would be the indices for drawing the quad. And you would use draw arrays. Excuse me. Draw arrays. Triangles. Now, suppose you wanted to generate a wireframe. Now, you can't just do the same thing and say draw arrays with lines, because that isn't going to get you the right lines. So you could say wireframe indices, and you would just take each pair. I mean, this is the simplest thing if you're going to generate this programmatically. You would just take each pair and put in 2 indices for the beginning and end of each line. So you would take, for example, A to B would be 0, 1. Then you would take B to C, which would be 1, 2. Then you would take C to A, which would be, 2, 0. And then you might take C to D, or C to D, yeah. Which would be 2, 3, and D to A, which would be 3, 0. So that would be a set of indices to take the same vertex data and render a wireframe, and you would use draw arrays lines. Of course, now there are ways you could optimize this, and typically the way you would do it in practice is you would, whenever you had a shared boundary between a triangle, you would actually draw it twice, because you don't want to go through the sorting process of figuring out exactly which ones have been put into the array already. And so we won't try to optimize it. We'll just do it in a simple-minded way. So that's the idea of creating indices to draw a wireframe. So what's next? We're going to take a look at normal vectors. And the idea here is you've got enough data to represent, let's say, attempt to sketch this. Say you've got a bunch of polygons, and making up some kind of a surface, right? Something like that. And there's 2 things to think about, right? Remember, we distinguished between the face normals and the vertex normals. And if we were to do this as a side view to make it easier for me to draw, the face normal means you've got something that is simply perpendicular to the triangle you would get if you connected each triple, making up a triangle, and just made it into a flat plane. In other words, take the plane determined by those 3 vertices and find a vector that's orthogonal to them. So these are our so-called face normals. And the contrasting situation is you maybe have the same set of points and logically the same set of triangles, but instead of viewing the triangles as planar, you sort of think of them as having a shape. So in the back of your mind, you say, well, I actually want this to look sort of like this, perhaps round. And so what you do is you choose a normal vector associated with each vertex that isn't actually perpendicular to either face, but it follows the contour, representing the illusion you want to create with the normal vectors when you plug into your lighting model. So these would be your so-called vertex normals. And as I remember, I did an example once for showing that you can just play around with these any way you want and create the illusion of a differently shaped surface from the same vertex data, right? Because it's the direction of the normal vectors that really create the illusion of shape. So the question is, how do I calculate these and how do I calculate these? And the first one turns out to be kind of easy, and the second one turns out to be also easy, but it takes a lot of work to see how easy it is. So let's think about this one first. So let me get another color. So the idea here is, first of all, how do you get a normal vector? And if you just look at one triangular face, let's say, and imagine you've got A, B, and C, and there's a convention that we haven't really had to think about yet, that we should become familiar with now, which is when you list the vertices of a triangle in your model, whether you are listing them by just putting the vertices in a certain order in your buffer, or whether you're listing them by choosing the indices in a certain order, there's a concept of the inside and the outside. In other words, which way is that polygon facing? And this makes a difference when you're calculating normal vectors, because the normal vector needs to point outward so you can check its interaction with the light. And so the vertices are always ordered counterclockwise. On the outward facing direction. So if I say this triangle is ABC, I mean that it's facing this way. If I said it was ACB, it means it was facing that way. And that'll make a tremendous difference, as you'll see in a second. So it turns out to be easy if you have three vertices in space, three triples of floating point numbers, to find a face normal, because you can just imagine you've got two vectors, namely B minus A and C minus A. And you know what to do next, right? If you have two vectors that lay on a plane and you compute their cross product, you'll get a vector that is orthogonal to that plane. And the only trick is, which direction do we compute the cross product? Because it's not commutative. It goes by the right-hand rule. So if I take, remember the right-hand rule is like this. If I take that cross that, then this is the result. So if I want this facing outward, I have to take this one cross that one, and then that'll be the result. And so my face normal let's say N is B minus A cross C minus A, those two vectors. And that'll give me I can't draw it, but it looks like that, right? Perpendicular to the face of that polygon in the direction we've chosen based on the ordering of the vertices. And the calculation for that is extremely boring. It's so boring that even though I've taught Calculus 3 before, I never remember how to compute a cross product. What I do is what we always do around here. Let me show you. We rely on a code library. So I think HeightMap.js. So there's a little helper function down here at the bottom of the skeleton for this homework that computes a cross product. And again, you've got 3 points, each one represented by a triple of numbers, fondly named A, B, and C. And this is the calculation of the cross product. And what it's returning you, again, is a JavaScript array containing a triple of numbers representing the coordinates of that normal vector. So that turns out to be pretty easy. And notice that we are normalizing it, right? In other words, we're taking the square root of, basically x squared plus y squared plus z squared here, and then scaling everything down by dividing out the square root so that they always have unit length. I mean, there's an interesting relationship between the cross product and the area of the polygon, but we actually don't care about that very much. We would simply like to have a normalized vector, unit length vector, as perpendicular. So questions about that so far? Yeah, good. So the next question, which, as I said, is not actually harder, but it takes a lot of work to realize that it's easy. So let's talk our way through that one. So what do we want to do to get these? And I think we sort of have to draw the picture. Who stole the green one? We sort of have to draw the picture over here. So the way you might imagine this is associated with every face. Remember, the vector is just a direction. So it doesn't really matter whether I draw it in the middle of the face, or whether I draw it at the corners, right? It's the same vector, same direction. But just for convenience, I'm gonna draw them as though they were sticking out of the faces. So we've got these little unit vectors sticking out at each face. Something like that. If you can bear with my drawing. And the thing is, we want to figure out what direction should be represented at that vertex if all I'm really trying to do is just make this simulate a smooth surface. And the usual trick you use is you just try to identify for a given vertex, what are all the adjacent faces? And you take those face normals and you average them. And the way we're going to do it, it's not strictly speaking an average. Excuse me. I said face, and I meant vertex. So the vertex normals is quote unquote average of face normals for all the adjacent faces, all the faces that include that vertex. So what do we mean by average though? It's actually simpler than an average. We're going to add up all of the vectors. I mean, just component-wise add them, and then renormalize so that it has length 1. And so we're going to add them up. And normalize. All right. So I would say that initially that might look like a complicated problem in the sense that it seems as though you would have to, for every vertex, go searching through the polygons to find all the ones that were adjacent, and then find their face normals and compute this quantity. But there's an algorithm for doing this that simplifies that considerably. And let's take a minute and see if we can figure out that algorithm. So what's our code going to look like? So it's we have something like this, that as you, the way we'll generate the vertices for one of these height maps is simply by essentially iterating over a selection of points in a grid in the XZ plane. And then for each point in the grid, we'll just generate, we'll have an X and a Z value for the point in the grid, and then we'll generate a Y value. So that's simple enough. And we'll lay those out in an array that'll look something like this. So there's going to be let's say a group of 3 numbers representing vertex 0, another group of 3 numbers representing vertex 1, another group of 3 numbers representing vertex 2, and so on. And eventually, you'll, let's say somewhere up here, you've got a group of 3 numbers representing vertex n. And notice that you can always compute the coordinates of those 3 numbers in the array, the indices of those 3 numbers in the array. Based on n, this is going to be index 3n, 3n plus 1, and 3n plus 2. So that's going to be an important relationship in doing the code here. 2, 3, 4, 5. Right, so this is vertex 3 plus 1, vertex 3 plus 2. Then we have 6, 7, 8. Vertex 2 times 3, 2 times 3 plus 1, 2 times 3 plus 2, and so on. So this is what we're going to generate as the raw data that you're starting with. And then there are 2 tasks to make this into a model. One is you've got to do another kind of iteration over that grid of points and choose the indices that will make the triangles you want. We'll do it with indexing and just generate each vertex once. And then the other thing is doing a different iteration over that grid to make the indices for the wireframe. And I think the way that I've set up the assignment is that you'll have the indices for the vertices, but not the indices for, you'll have the indices for the model, but not the indices for the wireframe. So you'll get to do that one. And likewise, I think that the sample code will include the code to generate the vertices, but not the code to generate normal vectors. So this is the algorithm you'll have to implement. So the idea is you now have you have the situation that you want to associate with each vertex one of these vertex normals that represented by this so-called average of the ones from the neighboring triangles, but you don't want to have to take each one and then go searching through the triangles to find the neighboring triangles, because that becomes difficult and extremely inefficient. It boosts it up to like cubic or something. So let's see about what it is we want to generate here. Would be a parallel array where at indices 0, 1, and 2, you have the normal vector for that vertex. 3, 4, and 5, you have the normal vector for that vertex. 6, 7, and 8, you have the normal vector for that vertex. So it's a completely parallel array, and conveniently you need 3 floating point numbers to represent the vertex position and 3 floating point numbers to represent the normal vector. So these are completely parallel arrays, which is convenient because you can use the same index calculation. And so the algorithm goes something like this, that what you do is you take your list of indices for the model. In other words, the indices that describe each face. And I guess, so if you think of, what is a face in the model? Well, it's three indices that describe one triangle. So these are going to be integers, right? Integer indices that's saying, all right, vertex 1, vertex 7, and vertex 9, that's one of my triangles, something along that line. So for each one of those triples representing a triangle, you would calculate the face normal for that triangle, which we know how to do with a cross product. I guess let's see if I can sketch it in pseudocode without getting confused. For each triple, and let's just, for lack of a better idea, A, B, C of integers representing a triangle that is a face. What do we want to do? You want to let's call it n1, n2, n3 be the normal vector for that face. Now the thing is, you have the indices for the vertices that face touches, right? That's exactly what those three numbers are. They are the indices in this array for the vertices that face touches, and therefore they are the indices in the normal vectors array for the vertices that face touches. And so what you do is you just add n1, n2, n3 to vertices A, B, and C. In other words, literally, you're going to take 3a plus 1, 3a plus 2, 3a plus 3, and add those three numbers to that triple in the array. Now, that's not enough information to get the normal vectors yet. But the thing is, you're going to go through and do this for every triangle. So by the time you are done with this loop, you will have accomplished that goal of taking every neighboring polygon for every vertex and summing up the vectors, the face normals in the associated chunk of three numbers in this array. So then when you're all done with this loop, what you do is you just go through and normalize each triple 3n plus 1, and 3n plus 2 in the normals array. Okay, so does this make reasonable sense? The first time I gave a similar assignment to this, I just sort of wrote the documentation and threw it at everybody and said, "You'll figure it out." But I thought maybe going through a little diagram might ease the pain a little bit. Let's take a quick look at the code and make sure I'm not overlooking something I intended to point out. So I mentioned the little cross product helper function because this is boring. There's, as you can see, very, very generous documentation. But yeah, so the overall picture is we're defining a class called heightmap, and the arguments are the function I'm going to use to generate the y values, how many points in the grid in the x direction, how many points in the grid in the z direction, and then the dimensions, the actual x and z coordinates for the bounds of this rectangular region. And so basically what we're going to do is just use these functions to generate attributes for the vertices, the count of the vertices, the indices for a wireframe, the indices for a mesh, and an array of normals. So that part's all done. generating the vertices, like I said, the this is fun, but I don't want it to get ridiculously tedious. So you can read this code to the extent that you're interested in, but basically it's just a nested loop. You iterate over the z values and iterate over the x values in what's logically this is a reasonable picture. What's logically just a rectangular array of points in 2 dimensions in the xz plane, generating a y value for each one. And when we say generating a y value, it just means we're going to apply that function f to the x and the z coordinates. And basically, there's the x, y, and z representing a particular point on our surface. And we just push those into the vertices array that you saw pictured up here on the whiteboard. Now, generating the wireframes, I guess this is interesting to read because that's not what I'm looking at. Oh no, I had it backwards. I'm asking you to generate the mesh indices for this version. And this is the code to generate wireframe indices. So the idea is if you imagine the triangles being laid out like this. So blum, 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 blum is a triangle and blum, blum, blum is a triangle. Then you're really just you're gonna push 6 numbers, right? Excuse me. 1, 2, 3, 4. 1, 2, 3, 4, 5. Yeah, you're generating 5 lines representing those 2 triangles. That one, that one, that one, that one, and that one. So you can kind of see how that loop works when you read the code. It's not profoundly complicated, but you want to do the same thing for the mesh indices, which is a little bit different because now instead of pairs of points representing lines, you want triples of points representing triangles. And so the idea is if you have any little square within that grid, right, at some x value and z value, then the way you would generate the points is again, it's described pretty well in the comment, I think. So you can write that loop. But I think that's all that needs to be said about this. Just, this is really the important thing, is that the fact that you're just pushing the x, the y, and the z onto a JavaScript array is what tells us that the vertices array is laid out the way I've described it, and that given the index for a vertex in that array, you just take 3 times that index, 3 times that index plus 1, 3 times that index plus 2, and that'll give you the actual indices for the 3 numbers representing that vertex. So, all right, hopefully that is clear enough. Adding anyone? Yeah, so again, what is our goal? It's something like this. I'll just sketch on top of here. Right? We want to take a face normal there and a face normal there, and all neighboring face normals for a given vertex. And we want to add them all up, right? For every adjacent face. So rather than iterating through the vertices and looking for the faces, we iterate through the faces, and every time we find a face that is adjacent to a vertex A, B, and C, we just go ahead and add that normal's coordinates to the corresponding entries for that face. So in other words, let's suppose, just as an example, based on what we have on the whiteboard, suppose that I had a triangle, say 0, 1, 2. Right, so 3 indices, a group of 3 indices represents one triangle in the mesh. And so what would I do? I would take that triangle and I would compute a normal vector, the face normal for that triangle, right? And that's represented by 3 numbers that I'll call n1, n2, and 3. And so what we would do then is we would take vertex 0 and we would add n1, n2, and 3, because that's vertex 0. And we know that because of the fact that I have a 0 in this triangle, it means that that face is adjacent to vertex 0. So that face normal needs to be added up as part of the faces that are adjacent. And likewise, we see the C there, that's vertex 2. So we would, again, at index 2, we would have right, plus n1, plus n2, plus n3. And the point is that by the time you've gone through every face and done all these additions, you have got exactly what you want, which is the sum of all the adjacent face normals for that vertex. And then you just go through at the end and normalize everything. Anyway, you've sort of got the algorithm here, so you can think it through with a piece of paper using this kind of reasoning, and I think it will become very clear. So A, B, and C are just indices, right? So literally, when it says a 0 here, it means the vertex 0 in my array, right? Yeah. Anyway, I think this is a good thing to think about. Is how normal vectors are actually generated. In other words, this is the kind of thing that actually goes on inside of Blender when somebody creates a model, because it really isn't practical to expect the modeler to manually configure each normal vector, right? So it's done by an algorithm like this. And so we might as well try to understand that and see if we can use it. So that is good. Now, what's next is I want to segue somehow into texture mapping, but there really is no natural segue. So I'm just gonna say, I don't know what, step off stage. And now for scene 2, texture mapping. Okay, so there's a lot to detail. The idea is really simple. We want to create interest in a scene by making things look more interesting and complicated than they actually are. And one of the ways to do this is to make things look like they have, say, a colored surface with a pattern on it. And that's really all it is. And I'm going to start with sort of a real world analogy and make the outrageous claim that, in fact, texture mapping was invented by IKEA. I'll show you how it works. So let's say you're a Scandinavian company and you're trying to manufacture cheap-ass furniture in China. And you want to make something that looks like a wooden coffee table. Now, of course, it's cheap furniture, so it's not actually made of wood. It's made of sawdust that's been glued together. Maybe we have some tapered round legs, something like that. But there's my cheap IKEA coffee table. Do a little bit. Cheap IKEA coffee table made of this pressed wood that is, again, sawdust and glue stuck together. Now, how do you create the illusion that it actually looks like wood? And the idea is something like this. You take a photograph of something with a wood grain, And chances are, your photograph isn't really as big as the coffee table. So you allow it to repeat. You sort of line up the images so that you can pretend it's a bigger image. And you put a coordinate system on this. Typically, let's just say you go from 0 to 1 here and 0 to 1 there, and then it can repeat. You can allow it to repeat the other way too, but let's keep it simple for now. And you say, well, why don't we take this portion of the photograph, maybe right here, and use that for the top. And just for simplicity, let's imagine that the top is logically going to consist of 2 triangles to make that quad. So we've got a triangle there. And you say, okay, well, that should be good. And you do the same thing with the other parts. For example, the facing here on the edges, you might lay those out slightly differently, like this, and so on. The legs are going to be complicated. Again, you might think of these as made up of little triangles. And once again, you're going to have to sort of figure out coordinates. In fact, so you kind of imagine unwrapping. Right? You can imagine this leg is going to start out as a cylinder, and then you'll snip it, and it'll start looking like this, and then you flatten it out completely. And then you plop it down onto your photograph or trace it out. And the thing then is that every point here has coordinates in this coordinate system. Right? So let's say that this point is at point 2, point 3. I'm just making something up. And maybe this one is at point 7, point 3. And so what this says is that if I'm going to lay it out, like that this point, this corner of that triangular face on the top of my coffee table is going to be associated with coordinates 0.7, 0.3. And this one, 0.2, 0.3, will be associated with that corner. And that's how we're going to keep track of where we are in that photograph. And you can also imagine that, partway through in here, I've got some coordinate, let's say ST, maybe halfway along there. And that might be associated with some location here. And the idea would be I'm sorry, I'm just catching up on the chat. So if there's a technique I experimented with when I was, basically playing with Blender, or maybe it was 3ds Max. You can take your model and actually do what I described here in the software, and it's very hard to do and to get right. But you can actually drag and position your mesh on this texture once you've got it unwrapped into a flat thing. And that's how a lot of it is done with these complicated looking, monsters and spaceships and yada yada. We're going to do really simple things at first, though. So these coordinates, right, that I've associated with the corners of this triangle, these are called the texture coordinates. So we would say that 0.7, 0.3 these are texture coordinates for this vertex. And so if you have this figured out, right, you've chosen a texture coordinate for each vertex, then what do we need to be able to do? we need to be able to put an image into GPU memory and then give our fragment shader the ability to sample from that image and use that somehow in computing the color to associate with that point, with that fragment in rendering the model. And that's basically what this whole texture memory mechanism is all about. Now remember what's going to happen. Again, now if we jump back into computer graphics and imagine this to be a model and this triangle I've drawn to be an actual polygon in the model, what is the fragment shader going to do at a point, at a fragment corresponding to somewhere that's not one of the vertices? And we know the answer to that is interpolation, right? The rasterizer can interpolate. And in this case, what the rasterizer will interpolate are the texture coordinates. And so at a point like this, the fragment shader can use an interpolated ST coordinate and use that point to choose where to sample from the image. So we'll try to see this in action, but you know, this is one of these safety glasses on kind of moments. There's a lot going on. The typical notation that's used in GLSL for texture coordinates is ST. It's generally going to be a two-dimensional array of data. Full OpenGL actually allows three-dimensional textures, but WebGL doesn't, so we aren't going to worry about it too much. I should point out, though, that when you look in other references, particularly in 3.js, you'll find the texture coordinates are often referred to as U and V, as well as S and T. Right? And in fact, I think in 3.js you refer to the texture coordinates as the UVs for that reason. So it's a bit of notational nonsense we have to get used to. So let's see. Let's do an experiment at least with how does this actually work? And what time is it? 9:54. I mean, 11:54. We have time for this example and not much else, but that's cool. Okay, let's kind of go through this. Get rid of that, get rid of that, get rid of that, keep that. All right, so here's an example to start with. We have this ability to load data into a region of the GPU that we're going to loosely call texture memory. And most often what we put in there is going to be data from an image. But I want to stress that it doesn't have to be an image. It can be any damn fool thing we want to put in there and sample from, because that's the key ability, is that within the fragment shader, we can sample values based on a texture coordinate that we can choose any way we want. So in reality, there's a lot of flexibility in how you use that memory area and that ability to sample. But let's start with just loading an image. So I'm going to take a really stupidly simple image. Let me find it for you. About Czech64 border. So you can see what it looks like. This is just an 8x8 checkerboard with a red border on part of it and a green border on part of it, just to help us figure out what it's doing when it's laid out on our model. And is it at the top? Oh, there it is. That's the one I want to use, I think. All right, so here is a very simple model, right? It's just our little square from GL example 1. And I'm just going to assign texture coordinates in the most obvious and simple way. Namely, I guess you probably can't see that from just the numbers. But if you imagine, the texture coordinate space is just a square that goes from 0 to 1 in the S direction and the T direction. And so I'm just gonna use the lower left corner of that coordinate space as the lower left corner of my square. The lower right corner of that coordinate space corresponds to the lower right corner of my square. So it should just take the image itself and paste it onto my quad. Wacky, wacky, wacky. All right, so that should be good. Now, so let's talk through some of the things that have to happen. Well, no, let's not. Let's look at the example first. And the first thing that's going to happen is, of course, this is going to fail. So I'm in texture.html. And of course, nothing happens. And I wonder if you remember why. Right? So we have this cross-origin problem, right? For security reasons, the browser does not want to grab data from your file system. And the simplest workaround for this is to just load it from a server. So what I typically do, and I recommend you do this too, unless you have a better idea, is documents ISU CS336_F19 workspace. And then if you have Python 3 installed and it's in your system path, Python -module http://server, and then a port number that is bigger than 1024, such as 2222. Yeah, and that sets up a server. And once you've set up a server, then you can load anything you want because it's no longer a cross-origin problem. So it's a slightly different command if you are back in the world of Python 2, works just as well. And this information is documented on our resources page. So now that we've done this, we can have a hope of loading this this texture example. I just have to go to localhost 2222 and texture HTML. All right, so there's our little square, but instead of drawing it in red or whatever, it's taking that image and just pasting it onto the quad based on the texture coordinates I've chosen. Now we could choose different texture coordinates and it would look a little bit different. For example, what would happen if I did this? I won't do anything crazy at first. But instead of going from 0, 0 to 1, 0, what if I just went over to 0.5, right? So halfway across the bottom, and then this would be 0.5. And same thing here, this would be instead of all the way to 1, it would be 0.5. So basically I'm saying I only want to use the left half of that image. And yeah, and so let's see what happens. So now what it's doing is it's sampling from the texture at values that were interpolated again along the lower axis from 0 to a half. So we're only going halfway across the texture, so it appears to stretch it horizontally. Now if we do the opposite, right? Let me comment this out. Yeah, what if we did the opposite? And we go, instead of to 0.5, we go up to, say, 2, right? Now, here's the thing. The coordinate region for texture space only goes from 0 to 1. So what happens if I start sampling from values that are bigger? And as you may know, if you've ever worked with images, there's two options. You can clamp the values to the edge, or you can allow them to wrap. And so let's do both. So the default is we simply allow the values to wrap around. So in other words, here I've got texture coordinate in the S direction, that is texture coordinate 0. Here I've got texture coordinate 1. And so the entire range of checkerboard image goes from 0 to 1. And then it starts over, right? Because we're going to allow our texture coordinate now goes from 1 to 2, but it's being wrapped around. And in a sense, we're doing modular arithmetic. And so the whole texture image now appears twice on the same region. And that's only one option. I mean, you also have the choice of simply clamping the values to the edge. And here, if we clamp to the edge, what's going to happen is it'll just be green, right? And you can choose to clamp or wrap separately in the S direction and the T direction. So let me clamp in the S direction. And so what's happening is whatever value is at the border there is just extended for the rest of the sampling because I have exceeded the limit of 1, which is the extent of texture space. If we were a little bit more, let's say, instead of going out all the way to 2, what if I went to, say, 1.5? And try it again. Right, so now it's wrapping, but it's only getting halfway across the texture. And I guess the same thing is going to happen when we choose to clamp in the S direction. Yeah, that's no different. Because the border is always going to be either red or green. I think, let me illustrate this example using a slightly different texture. If we go back to a checkerboard that doesn't have a border, maybe this will be more interesting. All right, so now you can see I've got 8 squares going up and down, but I've got 12 squares going across. And if I clamp, if I clamp, again, it takes whatever sample value you have at the edge at texture coordinate 1 will simply be continued, if that makes sense. Now it gets a little bit more interesting when you do not have this perfect correspondence between the shape of the quad that we're drawing and the shape of the texture region. Like, let's think about what happens if instead of a square, let's comment out the original coordinates and do this. So if you look at what I have here, I've got minus 0.5, minus 0.5, plus 0.5, minus 0.5. So the bottom is the same. But then I'm going to go, instead of going up to 0.5, I'll go up to 0.25 for my vertex position. So I'm essentially drawing a trapezoid instead of drawing a square with those two triangles. And that looks a little bit wacky. And part of the problem is a checkerboard is the most unforgiving texture you could possibly try to use. And that's why it's always used as kind of a test case for, have I got my texture coordinates laid out in an intelligent way? And you wouldn't want to do this in practice, but it does illustrate one thing that we know, that we keep forgetting, is that interpolation is always done one triangle at a time, right? So the interpolation done across here, it's the interpolation of the texture coordinates that we use to sample from the texture, right? This is done completely separately from the interpolation across the other triangle. So there's really no coordination between the two. So this would be a bad choice of texture coordinates if we wanted this to look like a checkerboard trapezoid. We would have to choose something differently, or go back and yell at your girlfriend in the design college. Don't yell at her. Sweet talk your girlfriend in the design college into laying out the texture coordinates differently. Other things that can happen. I mean, even just going back to our square, the way we had it. You can do wonky things with texture coordinates, and maybe let's try a few. Like, what if demonstrates wrapping. Yeah, this is a good one. So if you look at the coordinates, it says that at the lower left corner of my square, I'm going to start in the middle of the texture and then go up to 1.5 on the X side. And again, if we allow wrapping, and let me put it back to the checkerboard with the border. What did I just do? Oh, no file name. You can see what's happening there is that here's my the texture coordinate for that vertex is at 0.5, 0.5, and we're allowing it to wrap. And if we clamp instead, it'll be like that. If we clamp in the vertical, it'll be like that. Right, just repeating the border value. So again, illustration of wrapping basically. Let's do something crazy now. And what if we think about this? So I go from 0, 0 to 1, 0, and then up to 0.51. So I'm only halfway across the top, right? And yeah, let's try it. I find it's often difficult to get my head around what's going to happen. But yeah, so we're sampling normally along the bottom from 0 to 1, and we're sampling in a sense normally across the top, except that instead of going from 1, 0 up to 1, 1 in texture space, I'm going from 1, 0 up to 0.51. So this is essentially the middle of the texture over there. So that's probably enough illustration on that for now. The way the textures are loaded and managed in the code is something I think we might as well just start next time, because I cannot do it in 5 minutes. I guess what I could do is I could show you what the key controls are doing, that setting these parameters is there are two things happening. Basically, if you look at when I was pressing the S key and the capital S key, we're setting a parameter called wrap in the S direction to the value constant clamp to edge, or we're flipping it back to the constant repeat. And you can see from here what you normally have to do to interact with a texture, which is like a lot of things. In other words, like the buffers other buffers we have been working with on the GPU. You allocate the memory for your texture, you load the image or other data into that memory, and what you get back from the GPU is an opaque handle that you can use to refer to it. And it's the same pattern here. Right, we're binding a texture to a binding point called texture 2D, just like we did with array buffers. And once the texture is bound, we can refer to that binding point, and it will set the relevant parameters for the texture that is currently bound. And so that's going to be the mechanism for interacting with textures on the GPU. It's the same sort of process of you talk about them indirectly by associating them with a binding point. When it comes to textures, the situation is somewhat worse than it was for buffers in the sense, and by worse, I mean a little more confusing, because there's actually a second level of indirection. But again, I think it's better to get into that next time. So what I would encourage you to do at this point is just download this example and play around with some of these textures and I mean, choices for texture coordinates, and try to get some intuition about the relationship between the coordinates that you choose and what you actually see when the texture coordinates are interpolated. All right, so that is the day one basic introduction to working with texture coordinates. There is a nice section in the Teal book, by the way, which I'd encourage you to take a look at. Once again, where things are kind of explained slowly and in a practical way. So you might take a look at that between now and Thursday. All right, so I would say, let's call it a day. Eh? See you all Thursday. Thanks a lot. Bye.